Hello everyone, I am Rizong Liu. Today's presentation would give a talk about our recent work, single to dual view adaptation for egocentric 3D hand pose estimation. This is a work of the University of Tokyo, and in this work we propose a framework to adapt the traditional single view hand pose estimator to dual view settings. As we know, hand pose estimation aims at predicting 3D hand joints from a single hand image, and here are some samples. However, most of existing studies only work under single-view settings, and such setting poses some potential challenges, such as limited field of view and ambiguity in depth. To address this issue, using multiple cameras can help better capture the hand shape, and here we compare our method with existing methods. Traditional single-view methods only accept single-view input and therefore has limited field of view. And existing multi-view training methods, they have a broader field of view, of course, but require multi-view data for training, which is quite expensive. And more importantly, during testing, the camera parameters must be known, and the same with training data, and this limits its application scenarios. In contrast, we propose a single to dual view adaptation method, and our method only requires common and cheap single view data for training, and our method is compatible with arbitrary camera poses without requiring any camera parameters. This page gives the workflow of our method. First, given the pre-trained single-view model, we input that into our proposed method and adapt it to an arbitrary dual-view setting. After adaptation, the model can predict more accurate 3D hand joints. In summary, our contributions contains the first single to dual view adaptation framework for egocentric 3D hand pose estimation, which we call S2D hand. Also, we propose a pseudo-label-based strategy for adaptation, and of course, we have achieved outstanding performance for arbitrary dual views. Before getting into our method, let's have a look at our problem setting. During adaptation, the input contains a pre-trained single-view estimator and several dual-view data, and the output is an adapted estimator, which is well adapted to dual-view settings. During testing, the adaptive model accepts input hand image from each view and output predictions for each view. And after that, we can average those predictions from both views to get the final prediction. The right part shows the camera layouts and samples. Now let me introduce the overview of our method. First, we can obtain the pre-trained estimator on single-view data. Then, our adaptation method adapts this model to arbitrary dual views. Well, the details of this method are as follows. We have two types of models, an estimator, which is updated dynamically, and its momentum version, which is updated by temporal average. The momentum model is updated much slower and therefore more stable. Both models can predict hand pose predictions, and then the momentum predictions with an rotation matrix R are input into our pseudo-labeling module. Here the R is initialized before adaptation, and it measures the rotation transformation between those two views. The pseudo-labeling module outputs pseudo-labels for each view, and then the pseudo-labels are used to generate loss functions and then update the estimator dynamically. The pseudo-labeling module contains two parts. The first part is an attention-based merging module. This module is derived from cross-view consensus, which means those two hand joint predictions should be consistent if they are transformed into the same coordinate system. In this module, we first use the rotation matrix R to transform those predictions into the same coordinate system. Then we generate joint-wise attention from heat map predictions. That joint-wise attention is multiplied into those two predictions, and then those two hand poses are averaged to reach the final pseudo label. We generate joint-wise attention from heat map because we observe that the hotspot becomes darker with the arrow increases. Another module is the rotation-guided refinement module. This module is designed based on the invariance of rotation matrix between both views. First, the rotation matrix should be a constant value. Then, we can also estimate the rotation matrix from the 3D predictions, which we call R prime. Theoretically, R prime should also be a constant value during adaptation, and it should be exactly the same with R. So therefore, we can adjust those two predictions to minimize the distance between R and R prime, and the predictions after adjustment becomes the pseudo label. In this work, we use multi-view data from Assembly Enhanced dataset, which contains 4 cameras. Therefore, we can construct 6 camera pairs from those 4 cameras. In addition to Assembly Enhanced, we also use some synthetic datasets for pre-training, including generated hands and rendered hand pose datasets. As for evaluation metrics, we have 2 metrics. The first one is traditional monocular MPJPE, and the second one is dual-view MPJPE. The dual-view MPJPE measures the error of the final prediction, which is averaged from those predictions from both views. This table shows the single to dual-view adaptation results for 6 dual camera pairs. As we can see, MPJPE drops notably for all the camera pairs. This table shows the comparison with the state-of-the-art adaptation approaches. Apparently, our method generates less error than existing methods. This page explains why we designed those 2 pseudo labels. As we can see, with error of the prediction changes, the rotation-guided refinement module reduces the error caused by another pseudo label, and therefore creating a complementary effect. The code of this paper is available on the project page, and for more exciting works, we look forward to your follows through our lab's QR code. Thanks for your listening.